But is that the best we can get? Or can we implement mechanisms to improve the throughput with better probing of the network for usable bandwidth? TCP CUBIC tries to improve this throughput with faster increase in the CWND value when it is possible. This means more increase in lower values of the CWND. TCP CUBIC increases congestion window size as a function of the cube of the distance between T, the current time, and K, which is a point in time when TCP window size will reach the max value of the window size. This will result in larger increases in lower values of window when T is still considered further away from the point where the maximum value would reach, and smaller increases when it's about the time. Note that this might have a different effect when congestion conditions in the network change. For example, what happened after point T3 in the figure, where the congestion seems to be substantially alleviated in the network. This allows higher values of the congestion window size compared to what previously expected. Therefore, the tuning of the value K has an important role on TCP CUBIC's performance. By far, we have discussed TCP Reno, Tahoe, and CUBIC. Can you find out which one of them is in use? So we learned the congestion control mechanisms in TCP and their effect on TCP throughput. But using these mechanisms, we are reducing throughput for congestion control. Aren't we killing performance? Is that all we can do? Note that congestion happens in the bottlenecks of the network. These links are almost always busy due to high usage from different sources. When bottleneck links are busy, increasing the sending rate will not result in increased end-to-end throughput. This is because more segments have to go through the same bottleneck, and therefore probably they have to wait more for the bottleneck to be available for them. Therefore, the changes in the sending rate of TCP does not have an effect on the capacity of the bottleneck. However, it has an effect on how busy it is, and therefore how long the packets sent from the source point are queued and the experienced end-to-end round-trip time. And remember, the longer the round-trip time, the lower the throughput, as the RTT was in the denominator of the throughput value. So, keeping the network uncongested could be achieved by limiting the sending rate. But since that decreased rate will hopefully help in alleviating the congestion, it will help keeping the RTT value at its minimum. Delay-based congestion control mechanisms work on this principle. Delay-based congestion control mechanisms, which are alternative congestion control mechanisms for TCP, try to avoid congestion and maximize throughput by measuring RTT and trying to keep it low with controlling the rate of transmission. TCP Vegas and BBR are examples of TCP deployments which use this method.